Thank you so much for having me. I'm really excited to be back giving talks again post-pandemic, and this is my first time in Utah, which as I'm walking around looking at things, I'm like, wow, this looks a lot like where I grew up, which is in Calgary. So kind of a nice home feeling for me here. So I'm going to be talking about the escape from Flatland, building languages of the future today. And I usually like to start my talks by giving some orienting quotes. So first one is essentially that language is not just a way of expressing yourself, but it's also a tool, an instrument for thinking. And secondly, if you have daring ideas, they might not be the ones that are successful, but they might start you down the correct path. So my name is Zelenka. I am everywhere on the internet as Expeed. I am the CTO at a company called Fission, where we are working on the post-serverless future, sometimes called far edge apps. And this will probably not make me very popular here, but our goal is to make backends and DevOps completely obsolete. Glad somebody's excited. My background is mostly in programming language theory, virtual machines, and distributed systems. As was just mentioned, I'm the original author of the Witchcraft suite of libraries, which mainly bring concepts from Haskell into Elixir, as well as Exceptional, which gives you a nice ergonomic error handling. I do a lot of work with standards these days, so I'm the editor of the User-Controlled Authorization Network spec, as well as having done a lot of work in Ethereum and Filecoin, multi-formats, and a whole bunch of others. I do a bunch of stuff with meetups. During the pandemic, we started some online ones, including the Distributed Systems Reading Group. So if you're into distributed systems, you like reading papers, please join us. So, as mentioned, this is my second MPEX keynote, and on the first one, I had lost my voice. I was just trying to really get through it, and I think that's probably why I watched the video in preparation for this one, and I keep doing the come at me bro during it. So I'll try to be a little bit more relaxed in this one. This is, in some ways, part one of two-part keynotes. Often with keynotes, you end up giving a lot of thoughts about, or talking a lot about the things you've been thinking about lately, and apparently I have a lot of thoughts right now. So this is the first half, which is the more practical side, the things that you can actually do, and then I'm giving another talk in 2 weeks about some of the more radical changes that I think that we could experiment with. So, growth mindset. We love Elixir. That's why we're here. But it's important to think critically about our tools, right? We want this to be the best possible ecosystem it can be, with the best libraries, the best tools, and the best experience. So, if we're going to change, we have to ask some uncomfortable questions and look at things and doing things in a different way. So if you come away with two feelings, I want you to feel dissatisfied and inspired coming out of this talk. So please hold the rotten fruit till the end. So, I think a lot about what the Beam does right. And it's actually quite a lot, right? We're ahead of the industry. Everybody else is borrowing stuff from the Beam, right? The actor model, supervision trees, right? And these are working their way out into other parts of the industry, which is fantastic, right? We like these things. We want them to be everywhere, right? We don't want to just hold these to ourselves. But that does mean that our lead won't last forever. So, we can keep doing what we're doing, and that's great, right? It's a good experience. But it does beg the question, where do we go from here? Where can we innovate further? The core problem that I see in our industry, so not just in Elixir, the whole industry, is that code today is needlessly difficult and complex. It's getting better, but it's too hard, especially if we believe that software is going to keep growing, right? It's that we currently have this specialized, essentially priesthood of people that know how the computer works, and a bunch of people that don't, is a problem. We currently can't produce enough developers fast enough, right? We can't turn them out of boot camps quickly enough. So we need to create code that is faster, more flexible, clearer, correct, and teachable. So how do we build more structure, more understanding out of existing parts? How can we take things and put them together in a way that anyone could walk into it? And that takes away the tricky parts of the code and automates them. Computers are much better at us at some things, and we're much better than them at some things. We want people to fall into the pit of success, which sounds scary, but the idea, basically, is if you stumble and fall, you're still falling into the thing that you wanted to do, right? So it might not be, say, semantically correct, the thing that you expect the code to do, but it's not going to crash. It's not going to get stuck. And ideally, we create languages and ways of working where bugs are not even possible. And I know that sounds impossible, but by shrinking our languages down to the subset of things that we actually care about, this is entirely doable. So we're working with language. And the thing to remember is that our wetware, our brains, haven't actually changed in quite some time, right? The actual physical hardware we're working with is the same. So why are we able to do all of these things, build buildings, create computers? And that's that we have better mental tools than we used to. Abstraction, so cave paintings, things like this, right, started appearing about 50 to 100,000 years ago. So we've been able to abstract things for a while. We just didn't have the tools. And the one simple example I like to give is if you've ever worked with Roman numerals, they're a nightmare. If you try to do addition or multiplication, right, it's really hard. And then we switched to Arabic numerals, just a pure positional number system. And that makes it so much easier. And so that's just a shift in the tool, and now we can think about much more complex things. We are in a space of all the possible languages and technologies, and we don't know where we are in here. Hopefully we're on one of these peaks, but we don't know which peak we're on, and we don't know if there's a valley next to us or another peak next to us. We're definitely not in one of these valleys where going in any direction is going to be better, because then we would be discovering things all the time, right? So we're definitely on one of these little hills. But the idea that we've hit the absolute maximum peak of what programming can do, I don't buy that, right? There are definitely higher peaks in this range. In 100 years from now, we're going to be writing code that looks different than it does today, because we're going to find new techniques, new ways of thinking about things. That, however, does mean that we have to leave this comfortable spot and go down a little bit sometimes and explore around, and hopefully we find that next peak. So the world is changing, and it's actually changing around us. All ideas start with the invention, the 0 to 1. And over time, they become a utility. Everybody knows about them. We expect the lights to turn on when we hit the switch. HTTP, we don't really think about. It just works. And we tend to play, as programmers, in custom to off the shelf. So we're either plugging things together or building things. We're not usually inventing them totally from scratch. But when you get all the way down to things being a utility, that creates a new basis, a new playing field for us to invent new things, and then the cycle continues. So I think that we need to take this new field and have a Cambrian explosion of different approaches. Some of these will bear fruit. Some of them will go nowhere, and that's fine. Others will be amazing, and others yet we won't even have seen coming. So sources of inspiration for the things we're going to talk about in this talk are things I've seen work in production. Old ideas, I feel like everything was invented in the 70s. Functional pearls, this is a collection of papers and ideas that are essentially given the seal of approval of this is a good idea. Programming language research, stuff that, especially from the last 15, 20 years. Distributed databases, other ecosystems, and underused Elixir features. Instead of a table of contents, I'm going to give you a little graph. So the high level, we're going to talk about embedded DSLs, broken down into 3 sections: code as data, managed effects, and active metadata, more or less organized in that order. And along the way, we're going to talk about a bunch of other things. Okay, we're going to talk about expressivity and modular languages and model testing and optimistic concurrency and all of these things. That looks like a lot for 50 minutes. But, oh yeah, and time travel, that little thing. But don't worry, it's just these 3 top topics. So, 1 million languages. We need to create millions of tiny languages to make them simpler and easier to reason about. But languages are a hard thing to build, and even worse is building all of the infrastructure and tooling and ways of thinking about them. So instead, we can take the tooling and infrastructure from some other language, like, I don't know, Elixir, and build on top of that. As a programming language person, of course, I see everything as languages all the way down. So at the very bottom layer, mathematics is a language. Physics is a language. Binary is a language. It's maybe not the best language for programming in. It's a little hard to reason about, but it can do everything, right? Above that, we of course have the actual chip instructions, the ISA, kernel syscalls, the beam, Elixir AST. Things that we normally think of as programming. Your library and frameworks, yes, those are languages too. And same with your application domain. And the user's graphic user interface, also a language. And of course, the way we speak, natural language. There are 3 big buckets, big models of thinking about languages. There's more, but these are the popular ones. The first one is called operational semantics, and this is how the machine thinks. So literally what we're going to execute, or what the next step in the virtual machine will be. Right? And that's things like C or Go, right? Rust has a lot of this too. We have denotational semantics, and this is the abstract mathematical view. What does this program mean mathematically? Is it describing a set? Is it describing a map? Right? Haskell, obviously. Prolog also falls in this bucket. And then finally, we have semiotic, the semiotic view of languages, which is more about, well, how can we make things look like symbols or natural language? So obviously, natural language at the top there, and SQL and APL. I think that Elixir did a really interesting thing by taking Erlang and pushing it up to something that is a little bit more symbolic, a little bit more like natural language, and having more of this idea of, well, we should care about how the person is going to look at the code. And that is probably a big reason why this long existing ecosystem suddenly took off. There's an overall trend of moving from this mechanical view up into natural language, but that is a one-size-fits-all approach, and there's all of these other areas, all these other niches that we haven't explored, or that there's smaller languages that do. When comparing these, people often talk about things being expressive or not. There's been plenty of flame wars on Hacker News and Reddit about this term. But there's really 2 senses of this. One is just purely aesthetic. What do I think it looks like? How do I feel about writing an idea down? But the technical term for this is actually quite precise. It's about the power of a language. So here's basic arithmetic. We can do a lot with this, but not everything. If we add assignment to that, this is a new thing. We couldn't do this before. Now we can assign things to variables, and everything continues to work. Reassignment is even more powerful than just straight assignment. Whether or not you want that is another question. Loops are things that we can't do with assignment and arithmetic. So that is now, if we add this to our language, that is now strictly more expressive. Recursion and loops are equally expressive. So we can express the same concepts in these 2. Even if, yes, the aesthetics of this are really nice, right? But it doesn't actually matter from a purely expressive direction. So can a language be too expressive? Is there an upper bound on this? And if you imagine that there's a circle of all the possible useful programs in the world, and then another one of buggy programs, there is this overlap in the middle. And so that's not to say that every useful program has bugs, but some do. And you have to decide when you're writing your own code where you want that boundary to be and how big you want that language to be. Because the bigger your language, the more likely you're going to end up in this blue section. These are two very dangerous commands. If we add these to our language, other things can happen. So system.halt, which is going to end the program in the middle of execution, or gotos. Now, Elixir itself doesn't have gotos, so I'll explain it here. But gotos give you the full capability of expressivity. They're the maximum bound. So they work like this. Here's your lines of code, and we're going to go from one to the next until we hit a goto. And then based on its argument, we're going to pick where we jump to. And it can be anywhere in the program. Right? That's super powerful. That's amazing. You can do really great performance optimizations with this. But it's hard to reason about, and you can actually jump outside of the program, which is, I guess, kind of like a halt, but not an intended one. People often talk about Turing completeness as being, this is a language that could express anything. But Turing completeness is an anti-pattern. Turing completeness is harmful most of the time. Okay? Yes, you want the outer wrapper of your program to be able to do things like infinite loops, but you don't want most of your logic to behave like this. So Turing has this tendency to show up where he's not always wanted or not expected. So as an aside, here's some accidentally Turing complete systems. The x86 move instruction, Vim normal mode, the border gateway protocol. It's totally what we want to have get stuck in an infinite loop. TypeScript's type system, Magic the Gathering, the card game. And it's conjectured, but not proven, that Unicode is also Turing complete. So the core lesson here is that the more powerful language is, the more expressive it is, the harder it is to understand, and the more bugs you can write in it. This is not going to put us in the pit of success. Right? So let's look at some really small languages, some focused small vocabularies. This is image manipulation, right? Rotate, scale, translate, pretty simple. Here is moving based on rotation and then distance. And then one for, like a retro video game, where you can move north, south, east, and west, speak to other characters, or listen. And if you're just working in, say, image manipulation, that's really great. It's really hard to write a bug in this, right? You're just going to rotate things. You're never going to crash. Right? You're never going to run out of database, right? But it has a small problem, right? It's maybe too small. So we want to be able to compose them. Isn't that strange that we'd be able to take different languages and stick them together? This is a metaphor that I like to use for this. So we have here two simple, very small things. We just have two lines and the ability to take intervals on those lines. And different intervals, that's fine. And that doesn't express much on its own, but if we put them together and we say these relate to each other in some way, suddenly now we can put points in 2D space, we can draw images, we can draw really complex images. We can add one more line, which we'll call color, and colorize it, and of course, time. So this is 4 lines, 4 components, and we've created all of computer graphics, which is pretty powerful, right? We can take these really simple things, stick them together, and now express really, really general things. So if we take this rotate, scale, translate, and these game actions, move, speak, listen, well, now in our video game we can do things like, I don't know, maybe there's a wizard who then takes the character and turns it upside down. The character goes, why is the world upside down? And they get scaled, right? We can do all of these more expressive things now that we couldn't do before by just moving, or by image manipulation not being able to be in an interactive video game. Building up and tearing down ASTs. Everybody has always wanted their own AST, right? So the shallow embedding of a language is when it's what we normally do. You see this in libraries pretty typically, right? You just have some functions that you call, and they work directly, and we're using the built-in AST in this model. And you can do all kinds of stuff with this, right? It's very powerful. It's quick. It's easy to get going. So here's one for building deeper data structures, right, with some types and all of this stuff. And so then you can write nice short amount of code, and it spits out much more code. Pretty straightforward. But a language and an AST can be whatever you want it to be. So Elixir's AST, remember from this stack, there's nothing special about Elixir's AST. It's just well suited for the kinds of problems that we're trying to handle, right? Running things on the beam. We can be anywhere on that stack. So we're going to do some invocation rewriting by running our own AST. So step one, build a game plan. Second, you can transform it, you can analyze it, maybe make some changes to it, and then tear it down. Where tearing it down is actually running the program. So here is another DSL, right? We're going to move, wait, and then in this section everything will be capitalized, and doing some of these actions. If you look at just this one subsection, we can represent this two ways. We can say this is a linear sequence of events, essentially like a time series. And in this one, we're going to say caps lock on and caps lock off as we go. Or we can maintain that nested structure and say, hey, here's some stuff that's going to be with caps nested inside. So this second one is literally an abstract syntax tree rather than just a pure list. How do we actually manage these? This doesn't have to be too foreign, right? We can make this look exactly like GenServer. So here's handle effect on wait, and it'll replace all of the waits with process sleep. Here's another one, replacing say with IO puts, and another for caps lock. And we're going to do, actually this function doesn't actually exist, but imagine that there was an IO ANSI caps lock function. The interpreter for this is pretty simple, right? You take those, you say run, and my module that's going to provide me the ways of doing this translation, and just run them, run a bunch of these for me. So now that is going to get translated into this. One of the big advantages of this, right? When I first looked at this, like, well, why not use a protocol, right? That's going to do a lot of this translation for you. And the main reason is canonicity. With protocols, you have a data type and it has a implementation, and just one. You can't change it. Wouldn't it be great to have libraries of implementations that you could mix and match as needed, where you could swap out, I want to run this in a test suite, and it's not going to actually send an email. It'll just log that it would have sent an email. So standard vocabularies, this is the same one we've been looking at, right? What is common amongst these? Well, mostly movement, right? We have rotation, scaling, moving things around. Yep, there's a little bit of interaction there too. But let's take just the movement part out. So if we want to have these reusable libraries, what can we abstract out? Well, we have some graph routing, we have some geometric stuff, right? And these can be shipped as their own libraries, and we can build our own DSLs on top of these. Remember, that whole giant stack from the beginning is how the languages work. We take the high-level syntax, we break it down to AST, it goes into beam bytecode, that gets translated into machine instructions, right? We're just adding more layers on top of that. Other really common ones are things that are set-like or partial orders. So these also, if we want them to run anywhere, they need to have laws. We need to know that they're going to be consistent because we wrote them in such a way that our expectations will always be met regardless of where they're used. So a partial order says some things might be related to each other and others not. The classic example is addresses. So I'm on First Street and there's house 1, 2, 3, 4, 5. And I can say that 5 comes after 3. And then I'm on Main Street and I have house 1, 2, 3, 4, 5. But the house that's on 3 Main has nothing to do with the house on 5 First, right? They might even be going in different directions. They're not directly relatable. And we can find that in all kinds of places, right? This is very, very general. And so as long as we make sure each node relates to itself, equal elements don't precede themselves, which is to say that if it's a thing, it's just equal. And that if A is less than B and B is less than C, then A is less than C. Pretty simple. Then this will work literally everywhere that you use it, and it'll match people's expectations. So yeah, it turns out everything's just math when you get underneath it. And that should not be surprising coming from the author of Witchcraft, but that's a lot of what that style is about, right? And so we still want to take these things, this math, and apply a more human-readable aspect on top of it. And so we can build those out of these basic components. Turing has also said that the most important distinction is between discovering something and inventing something, right? And these basic ideas, things like set unions and partial orders, are so general that they seem to be almost baked in to the universe, right? They are discovered, not invented. But we still need to go deeper. So let's get rid of our effects. Simon Peyton-Jones has said, have no truck or have no business with the grubby compromises of imperative programming. I am pressing the button too many times. There we go. So Elixir, when I was first learning it, almost a decade ago, I found that it was actually like surprisingly imperative, right? We get all of the nice, pure functional stuff, but it's very practical, right? So we still have the ability to just send an email right to the database. But if you want to have that nice equational reasoning, you can place it wherever you need to. Wouldn't it be nice to have that in more places without losing that easy side effects? So impure functions, or procedures, produce side effects. Impure functions only manipulate data. So this is a function, right? We've all seen this before, right? Function has input and has output, and then there's another function. And then we have these side effects that come in, plug in from somewhere in the outside world, or they escape out after. And the basic idea here is, let's push that as far out as we can until later in the program. And in the meantime, then, we get to work in this purely functional, really easy to reason about, easy to test world. Here's the 4-layer diagram that goes with this. At the bottom, we have data. Data is extremely stable. Data doesn't change. Above that, we have pure functions. Pure functions take data and produce more data. It's a little bit less stable. Above that, we have managed effects. They're represented as pure code, right, or as pure data, rather, but can be interpreted by a runner as some kind of effect, like a side effect, but managed. Shocking. And finally, we have imperative code, which is direct access to the real world, but is extremely unstable, right? And so we have this information through to action spectrum. If we want to take our actions and make them totally pure, well, we've actually already been doing this entire presentation, right? Taking this with caps and saying all of these things and turning that into something that is later run or later transformed at call time makes our lives much easier, because things like, and this is my favorite example of this, right, is doing testing. So testing a database or testing a network connection and having to record what the output of that's going to be is really difficult and mocking, right? It feels messy. But if we can test on just pure data, right? So we have this thing, we're going to have our runners there at the bottom. Well, now we can just output our own AST and just inspect it directly and say, these are the things that will get run. Or replace instances of the runner for these with simplified versions that just output to a log or write to an agent. And now we have this log of what would happen without having to say, hey, don't actually send an email. How far can we take this? So implicit parallelism, we do obviously a lot of concurrency in Elixir, but it's really low level, right? We know about, here's all the process IDs, we're sending messages around, and it's a very sequential way of thinking, right? We have this exact order of events that are going in. Humans are very good at sequential reasoning. We like to think that there's just this one sequence, but a lot of the world isn't, right? And in Elixir, we try to, as much as possible, ignore this, except for when we have coordination between things. And coordination is actually extremely painful and usually avoided or dumped into a database or somewhere else. And we have to handle it in a special way. This is throughput of our system and the number of parallel machines that are working on the problem. And because you have to do this coordination, you have to say, hey, give me something else off the queue, or no, wait, I'm still working on this data. We get lower impact from having more processors. It's actually, or more machines for that matter. It's actually even worse than this, because as soon as you have incoherence or data contention, we actually drop off. So getting the wrong result back can have this cascade failure. Having to rerun things in an uncontrolled way where we're having to do the coordination can have this cascade where we actually lose performance versus not having it be parallel. The Church-Roster theorem, really old idea, says that if we have some pure function, the order that we evaluate the arguments doesn't matter. Right? So here's a little control flow graph. The top is just the start of the computation. And we say, well, bar and baz gotta go off to the sides, and then we're gonna bring them together. And it doesn't matter if one comes before the other. And this implies, luckily, that if we have lots of things happening on one of these sides, then we can commute where this blue dot happens among these. So here are possible orders that these could happen. Here's the linear sequence of time in which these happen that are all equally valid, right? The code that produces this says we're actually going to relax that constraint. But it's very easy to look at the code, right, like on the left here, and say, oh, I know which ones of these have a dependency on each other. We just look at the AST, here's an assignment, here's where it's used. Simple. So we can do a dependency analysis on this relatively complex code. And here's what depends on each other. It's pretty straightforward. Which means that we can take anything here that is off to the side and run those completely in parallel. We don't need to know about this in advance. We can let the machine handle this for us. We can also take anything that is in enum and automatically, if we're mapping over it, we can automatically parallelize that as well. So if you have a long-running process, you can take this, right, wrap it in some task asyncs, and then await them. And instead of having each of those things wait, you can get very, very high speedups. In fact, we shipped this in Witchcraft, and the benchmarks, I mean, obviously we're cheating, right, because we're taking sequential things and making them totally parallel. But in the benchmark suite, we can get multiple orders of magnitude speed up, even with relatively simple code for long-running things. Actors are really great, right? They have their own bit of data, and they have some messages. And they have messages in the queue. And when they're running in total isolation, everything's just fine. But when we want them to talk to each other and coordinate and say, hey, we need to have these two bits of data update at the same time or not at all, then it gets tricky. So what do? We tell the other one, hey, don't accept messages from anyone else except for me for the next little bit. And we're going to exchange some information. We're going to do some computation. And then one of them crashes. And then because it's in a supervision tree, hopefully the other one crashes, because otherwise we end up in this completely nonsense state. Right? And that's not great. And the way to make this better is to reduce the amount of time that we're doing this coordination. Right? It's called the critical section. Make that as small as possible. Optimistic concurrency has multiple solutions to this. My favorite is software transactional memory. When I started working with STM, it just blew my mind. It makes things so simple. So here's that example I just gave. So we're going to have some money being transferred, right? We're going to do some compute. This is the critical section. And then say, OK, yeah, that worked, and then release those locks. And of course, we want to make that as small as possible. So adding a couple more steps in here we can make that middle section really short, and we can also automate that. So here's the same picture. We're going to copy the data from both sources, so that's a read-only operation, and we're going to keep the counter and say this is at timestamp 1. Okay, great. Here's the my time in this, or my data in the series of time. I'm going to do some computation on that, and I'm going to say here's the new balances that I come up with, and then I'm going to try to acquire a lock on both of these other processes. And if the data in the meantime has changed, okay, we blow up and we try again. We grab the new data and we retry. Nothing has actually been affected yet. We're not going to get into this bad state. When we finally acquire those locks, we do those writes. We do really minimal stuff in the critical section, like as little as possible. Literally just say, hey, store this thing for me. We get that back okay, and then we get the unlock. And the high-level syntax for this is really simple. You put transact around it, just like you would in a database, right? This is literally a database transaction abstracted out to, or generalized to, all code. You may have seen the dining philosopher's problem before. This says that there's a bunch of people trying to eat a meal, and they each have a utensil, often a chopstick, on either side of their plate. And in order to eat, they need to have both of them. So there's the problem, though, that there's not enough for everybody to have to be able to eat at the same time. This is a classic concurrency thought experiment. And instead of having to do all of this coordination and figure things out, well, now your programmer, or your end user, only has to write, I'm going to fork the world in a world where I take both of them, I eat, and I put them back down, and we're going to try until I can actually acquire both of them. This becomes really, really simple. So transactions everywhere. It's a different way of thinking about this, right? We're no longer in that mechanistic worldview, right? We're now just talking about the end result that we want to get and letting the machine figure it out for us. Finally, just a couple of slides on metadata in motion. So we've had this whole idea about effects. What if we go the opposite direction and have data provenance? And the main thing to remember about data provenance is that's from the Provence region of France. Otherwise, it's just sparkling metadata. Proof carrying code. So you have a list, and you want to get the head of the list. And that's a dangerous operation, potentially, right? Maybe now you have to deal with all these nils. And now you have to stick it in a case statement and do all this extra work. Well, what if you checked that already? Well, now I have to check this all the time. That's really annoying. What if I wrapped it in a non-empty list that kept the head separate from the tail? And now it looks like this, and I can wrap this in all of my protocols so that it works like a regular enum. Except now in enum, where I don't have to worry about checking, is there some data there? There's data there. We can also do this with things like sorted items. If you're doing a lot of sorting and merging, so for example, a merge sort, once it's sorted, and we have two of these, merge sort becomes trivial. The hard part is if they're scrambled. So once I've sorted it once, why should I ever sort it again? I can just attach some metadata to it, wrap it in some metadata, and say, hey, this has already been sorted. I assert that this has been sorted. Capabilities. Doing access control is really hard, right? We have all these rules in our database. There's so much happening with them. We always add more, and we have to push everything through a central source. The other model of this is capabilities, where you pass around some data along with your request inside of your code, and when the handler sees it, says, okay, I'm allowed to overwrite this directory. I'm allowed to send this email. And it doesn't have to do any additional go out to the database and check. It just goes, here's the bit of data, that's the proof that I was allowed to do this. And I know that this was passed to me because this only exists inside of the code, and in fact, here's the user out of the database that I looked up once. And this is the actual usage of that, where we take one of these and we require it. It won't even work unless we pass it one of these can-do things. And provenance. So sometimes, other than logging your data, it's useful to know what the previous values were. This is really useful in testing, for example. But you can also have a branchable history. So once you have this history going back in time, here are my previous values, there's nothing that says that, well, what if I rolled back and tried something else? That's entirely possible as long as you hold on to that data, right? This is just a really simple way of managing time travel. And is much easier than, say, doing a debug log, because that's not interactive anymore. You can't actually do anything with that log. You have to reconstruct that state. Quinn, in the last talk today, is going to be talking a little bit about data log. You can go really far with this idea, where you abstract out all of the states into a database of individual small facts, and then create new views over that state over time, and say, essentially doing queries into it, but keeping a log of, hey, these are the bits of data, these are the subsets that I knew about at this time, and then fork your histories, change things around, and have one unified model where you're not doing this completely manually. Right? You can even do this in a totally distributed setting. So, wrapping up, some tools for the intrepid among you. Main thing to remember is that programming languages influence the way that we think. They are a tool for thinking. Changing your language to say the things that you want to say and nothing else increases the likelihood that you will say the right things. So, experiment with adding structure and dimension, making reusable DSLs, managing your effects, mechanizing away the hard stuff, and passing around context. Is this the future? I don't know, hopefully. But we need to experiment with more directions and try new things. These are a couple options. There's a vast array of things to experiment with that I have not seen in most languages. So go explore and share what you find. Thank you.